We spend a lot of time in statistics talking about the average score, the average price, you name it. But sometimes the average doesn't even tell half the story. Sometimes what you really care about is consistency. So today, we're going to tackle a different kind of question. How do we measure our confidence, not in the average, but in the spread or variability of an entire population?
I mean, think about it. If you're a manufacturer making parts for a car engine, you don't just care about the average size of your parts. You need every single one to be almost exactly the right size. An average that's on target but has a huge amount of variation is pretty much useless, right? So how do we actually put a number on our confidence in that consistency? Well, the tools we use for the mean just won't cut it. For this job, we need something totally different.
And that new tool is the chi-square distribution. Yeah, the name might sound a little intense, but trust me, it's a super powerful key that's been designed for one very specific purpose: to help us understand a population's variance.
So what exactly is it? Well, the chi-square distribution, and you'll often see it written with that Greek letter chi squared, is basically our go-to method anytime we need to take a small sample and make an educated guess about the true variance of the whole population it came from.
Okay, so this is where the chi-square distribution starts to get a little weird, because it doesn't really follow the same rules as that nice symmetric normal bell curve we're all used to. It has three key properties you have to know. First, its values are always 0 or positive, which makes sense, right? You can't have negative spread. Second, it's not symmetric at all, it's always skewed to the right. And finally, and this is a big one, its shape isn't fixed. It literally changes depending on the size of your sample, or what we call degrees of freedom. For example, have a look at this. When you're working with a really small sample, which means you have low degrees of freedom, the curve is all bunched up near 0 and has this long tail stretching out to the right. This is exactly what we mean when we say it's skewed to the right. But check out what happens when we start collecting more data. As our degrees of freedom go up, the distribution starts to spread out and becomes much more balanced, much more symmetric. It's almost like it's trying to grow up into a normal bell curve, even though it never quite gets there. So how do we actually use this funky-looking distribution to build a confidence interval? Well, if you're comfortable with that simple point estimate plus or minus the margin of error thing we do for means, you might want to brace yourself. The formula here is a little different.
And here's why it's different. Remember, for a mean, the interval is symmetric. We take our sample mean and just add and subtract the same amount to get our bounds. Simple. But because the chi-square distribution itself is lopsided, our confidence interval for the variance has to be lopsided too. It's asymmetric, which means we have to calculate the lower bound and the upper bound as two separate problems. So here's the formula, and I want you to pay really close attention to the denominators. See how the numerator, that n-1s squared part, is the same on both sides? But look at the bottom. The chi-square values are flipped. The bigger chi-square value from the right tail goes under the lower bound, and the smaller value from the left tail goes under the upper bound. I know, it feels totally backward at first. But remember, when you divide by a bigger number, you get a smaller result. So it actually makes perfect sense why it's set up this way.
Now for some good news. After you've done all the heavy lifting to find the confidence interval for the variance, getting the interval for the standard deviation is the easiest step of all. You literally just take the square root of the lower bound and the upper bound you just calculated. That's it.
All right, that's enough theory. Let's get our hands dirty and see how this works with some actual numbers. We're going to go through it step by step.
Okay, here's our situation. Let's say we've grabbed a sample of 25 items, and we've calculated a sample standard deviation of 4.2. We want to be 95% confident in our final interval. The first thing we need is our degrees of freedom, which is just our sample size minus 1, so 24. Next up, we got to find our critical values. Since we want 95% confidence, that leaves 5% for the tails, which we split into 2.5% on each side. So you'd go to your chi-squared table or pop it into your software, look up 24 degrees of freedom, and you'd find two very different values. 12.401 for that left tail and a much bigger 39.364 for the right tail. And now we just plug everything into that formula we saw earlier. And look, you can see that counterintuitive flip right here. For the lower bound on the left, we're dividing by that bigger number, 39.364, and for the upper bound on the right, we're dividing by the smaller one, 12.401. You run the calculations and voila, we get our interval. This tells us that we can be 95% confident that the true variance for the entire population is somewhere between 10.755 and 34.139.
And now for the easy part.
To get our interval for the standard deviation, we just take the square root of those two numbers. And there we have it. We're 95% confident that the true population standard deviation is between 3.280 and 5.843.
Okay, before we wrap this up, there is one absolutely fundamentally critical warning that comes with this entire method. Seriously, this is the one thing you can't afford to get wrong.
Just let that sentence sink in for a second. Not robust to departures from normality. Unlike some other statistical tests that can be a little forgiving if your data isn't perfect, this one isn't forgiving at all.
So let me translate that into plain English. If the population that you took your sample from doesn't follow a normal bell-shaped distribution, then that confidence interval you just worked so hard to calculate is pretty much useless. The entire method, all of that math, it all depends on this one single assumption of normality.
Which leads us to the most important takeaway of this whole explainer. Before you ever start plugging numbers into this formula, what is the absolute first thing you must always check? You have to verify that your sample comes from a population that's at least approximately normal. In statistics, your assumptions are everything. Don't ever forget to check them first.